We present DiWA, Diffusion Policy Adaptation with Word Models. In humans, dreaming is associated with an enhanced ability to solve next-day problems. This ability to sleep on a problem and wake up with clarity inspires this work. Diffusion policies are powerful, but they inherit the core limitations of imitation learning and are limited by the narrow scope of expert demonstrations. Online reinforcement learning can fine-tune policies, but it's sample inefficient and risky. Needing millions of real-world interactions makes it impractical for real-world robots. In this work, we fine-tune policies entirely offline within a learned word model. By generating imagined rollouts in latent space, the robot practices in a dream, improving its skills efficiently. The training process of DiWA consists of 4 phases. In the first phase, we train a word model on unstructured play data. This model captures the environment's dynamics in a compact latent space. Next, we pre-train a diffusion policy on expert demonstrations by encoding them into latents and learning to denoise them into actions. The word model lacks task rewards, so in phase 3, we train a binary classifier on expert latents to predict success and provide rewards during imagined rollouts. In a final phase, we fine-tune the diffusion policy using policy gradients on imagined rollouts in the dream diffusion Markov decision process, enabling efficient skill adaptation entirely offline. To evaluate our approach on real robots, we collected 4 hours of teleoperated play data using a Franco robot in a tabletop setup, recording multi-view RGB, proprioception, and actions to train our models. Here we see the first skill, opening a drawer. On the left, the pre-trained diffusion policy often struggles to complete the task. In the middle column, we show imagined rollouts within the word model's latent space, where the robot adapts its behavior offline. On the right, we see the result of this dreaming process. The fine-tune policy now reliably opens the drawer, all without any real-world interaction during fine-tuning. Next is the slider task. Again, the pre-trained policy lacks robustness, it misses the handle and fails to complete the motion. In the center, we see the policy refining its behavior through imagined rollouts in latent space. By the final column, the fine-tuned policy performs a smooth and successful push. Finally, in the closed drawer task, we observe the same pattern: initial failure, offline fine-tuning in the latent space, and successful execution. Across all 3 skills, the robot improves without touching the real world. Here is the summary of the quantitative results. The graph on the left shows how the policy performs in the real world with respect to the number of word model interactions during fine-tuning. On the right, we report successful policy improvements across 8 skills in Kelvin environment D. To achieve a similar improvement across 8 skills, DPPO, which is the latest state-of-the-art online diffusion policy fine-tuning baseline, requires close to 2.5 million environment interactions in total. DiWA, on the other hand, requires no environment interactions at all. This highlights the power of our approach, combining diffusion models, policy gradients, and learned word models to adapt skills safely, efficiently, and entirely offline. Thank you for your attention.